So I want to just say something now about entropy and heat flow. Um, so let me, sorry. So if we take an endothermic process, we're referencing the system here, right? So if we take an endothermic process, delta H is greater than 0. The system, from the point of view of the system, it's endothermic. So Q is plus. But from the surroundings, Q is negative. So from the perspective of the surroundings, it's exothermic. So heat flows from the surroundings into the system. We're talking about the surroundings now. Focus on the surroundings. The temperature of the surroundings decreases, and the average particle motion decreases. And so if the motion decreases, that's introducing order, so it's decreased disorder in the surroundings. So delta S for the surroundings is 0. So we're going, when we have an endothermic process in the system, the surroundings are having a increase in order because their surroundings are cooling down. They're cooling down, and it's more orderly. So delta S is negative. So why am I focusing on the system? I'm sorry, on the surroundings. Because the endothermic process of the system could be anything. The system could be just a temperature change, or maybe it's a chemical reaction, or maybe it's a physical change like melting or freezing. And we can take a look at that on its own. But in terms of the surroundings, whatever was going on in the system, there's exchange of heat with the surroundings. And we want to know what to expect for the surroundings. So the opposite process, if it's exothermic for the system, delta H is negative. So Q, if it's exothermic, Q for the system is negative. And for the surroundings, Q is positive. The surroundings are absorbing heat. So the heat is absorbed by the surroundings from the system. The temperature increases in the surroundings. Average particle motion does. And so we have increased disorder, which means, of course, delta S is positive if you're increasing disorder. So I want to go back to the concept of, we looked at the units in entropy, and the units were joules over Kelvin. And remember I said that it's the exchange of heat due to energy dispersion at a given temperature. So what does that mean? You take the heat flow into the surroundings and divide it by temperature. So how should you think about this? Well, look at the distributions in this figure here. If you're at a low temperature like 300 Kelvin and you go to 600, look at the big difference in the shape of the energy distributions. Okay, the purple and the green. So if you go from 300 to 600, there's a big change in distribution. But if you go from 900 to 1200, look at the two distributions. Not so significant a difference. So the change in entropy, if you have the same amount of heat flow into the surroundings, you're going to increase the entropy. We'll talk about that. It could also be flowing out and you decrease entropy. Either way, let's talk about increasing entropy in the surroundings by having heat flow into it. The effect on the entropy from that amount of heat will be greater at a lower temperature. At a lower temperature, you'll have a greater impact. So the analogy I always give is, let's say you had a side job on the weekends, you mow some lawns, and you always use that money to throw a party every week. So it's just fun money, right? So when you have a party, there's all this chaos and motion and people running around doing things. And let's say you make, $200 a week working on the weekends, and you spend it all on a party. So you're able to buy all these things to do at the party, and people are having a good time. And then one week you get an extra $200. So you actually can double the things to do and experience at your party. So there's even more commotion. People are even more excited, twice as excited. But what if you got $200 extra, but you usually make $2,000 a weekend? Well, yeah, it's a little extra money. The party's going to be a little bit bigger, but is it going to be a noticeably larger amount of chaos? Not as much. The party's going to be about 10% more chaotic, as opposed to doubling the chaotic nature of the party if you double the currency. So the currency is like the heat in that regard. So the equation that we just talked about for the surroundings, okay? You see, we're going to want to focus on the system. So there's some relations that we can look at here. First of all, the heat exchange is equal and opposite. So the heat of the system is equal but opposite that of the surroundings. So if the system has an exothermic process, the surroundings will be endothermic. The quantity of heat will be the same, opposite sign. So if we're calculating delta S for the surroundings, we can relate that to the heat of the system, which will be equal but opposite. So we get a negative sign there if we reference it to the heat flow of the system. Well, that's nice because you might be able to calculate the amount of heat coming out of the system. So if we're working in a constant pressure, Q is delta H. And that's really nice because, like I said, delta H might be something you can calculate. Maybe there's a chemical reaction, for instance. So for instance, what if we had an exothermic reaction? Delta H for the reaction is negative because it's exothermic. So the surroundings, of course, are going to be endothermic, right? So yeah. So if you plug that in, delta H reaction, there's a negative here because we're already relating the surroundings to the system. So there's a negative there already. The delta H is equal to the heat because it's constant pressure. So if the delta H for the system, or the Q for the system, is negative, that means the heat for the surroundings will be positive. Now, if this delta H is negative, then the delta S for the surroundings will be positive. Okay. Why is it positive? Because if it's exothermic, so here's the reaction, here's the surroundings. The heat flows into the surroundings and increases the entropy of the surroundings. Now, if you have an endothermic reaction, delta H is going to be positive. We already have our negative in this relationship because we're relating surroundings to the system. So it's equal but opposite for the heat. If this is positive because it's endothermic, so now we have the reaction and then the surroundings. The heat flows in. And so what's happening to the surroundings? The surroundings are losing heat, less motion, more orderly. And so delta S is going to be negative, which means it's becoming more orderly, not disorderly.